So, looking at the IR for this compound, what are the notable peaks that stand out to you, Nelly?
One at 1700, the carbonyl one.
Right. So carbonyl group, good. Any others?
CEA.
Solomon.
Yeah, the peaks at 3,000.
Yeah.
NCEA.
So that's about it, right? So based on this, what are some possible functional groups our molecule might have? Or like, yeah.
Aldehyde.
Could be an aldehyde.
Ketone.
Ketone, yeah. And why can't it be something like a carboxylic acid? What's it missing? Nelly?
There's no OH.
Yeah, no broad OH stretch. So not only are we looking for what's there, but what is not there to help us narrow it down. Cool. So those are the two notable peaks. That's about it. I think I was talking over here with Annabelle, and she pointed out that there is no halogen stretch down in the fingerprint region, right? So she was looking really closely. Is there even a chlorine or anything on the molecule? So you look down there in that messy fingerprint region. This is actually pretty clean for once in this spectrum. But yeah, you said, oh yeah, there's no chlorine or halogen or anything. So that's another thing we can discount. That's cool.
Which means you know that it will be an alkyl group.
Yeah. Okay, let's move on to the CNMR. What information can we get from this? Tell me something.
We have 4 unique carbon environments.
Yeah, thanks, Ben. 4 unique carbon environments. Anything else it can tell us if we're looking at particular peaks? Yeah.
Well, the 3 at the end are all alkyl, and you got one at like 220, which is probably ketone, or maybe an aldehyde, because we ain't got a little marker, so probably ketone.
So it's really downfield.
Mm.
That's the word we want to use, and it's
Downfield.
de-shielded because it's probably the carbon attached to the oxygen. And you said all of these are alkyl carbons. That's
Yeah.
really awesome. So they're more shielded, they're more upfield. Okay, that's about all we can do with that right now. In the justification section, we want to talk about each individual peak a bit more and what's attached to them, and we'll look at that very soon. And the last spectrum, the mass spec. So what's the very first obvious thing we want to know from this?
It's a different picture.
Yeah,
Thanks.
that's not
Yeah,
how.
yeah, that
Oh,
one
did I
says
show you a different
27, this one says 51.
Okay.
Whoops. It's 74 is your
Hold on.
You just meant from the one that
Hold on.
Their IR and they're different. And I was like,
yeah.
Oh no.
yeah, that's what I
I
thought too.
literally when she was like, what's the difference between these two things? I'm like, that one's spelled different. Like, that's not the answer.
Okay.
One's not wrong.
Good.
Hold it there. No, that's not what we
Here we go. That one there. I'll fix up the slides later. But anyways, so on this one here, we see the mass spec. What information can we get from that? A really obvious information we're looking for right away. Yeah, Ben?
molecular ion is at 86.
Correct.
So we know that's going to be our molar mass.
Perfect. Exactly right. And the little blip to the right is just some of the molecules that contain a carbon-13 isotope. Okay. The other things we want to do in our justification report is explain what the fragments are that produce some notable peaks. Like the base peak should always be one that you explain in your report in terms of what the structure of the fragment was that matches up with a base peak of a mass of 43, I think here. Yeah, 43. Cool. And maybe 1 or 2 other fragments as well. So I'm looking down at 15. 15, that always tells me it's a methyl group producing that. So a methyl group's fallen off the molecule. There's one at like 27. We could maybe figure out that one. And that's about it, all we got to do. In the report, I'm expecting you, for excellence, to propose structures for 2 fragments. So the base peak can be 1, and then like the methyl group's kind of a cheat option because it's pretty easy. But if you want to be more challenged, maybe justify one of the other peaks, you know?
In this case, the base peak has 2 associated with. Yeah.
There are 2 fragments actually that contribute to the base peak.
So could I cheat again and just do?
No, you
And
got to
then
talk
we've
about
got
2
the
peaks.
methyl group, and then there's 2 cheating, which adds to me.
Can we
Oh.
cheat the molecular ion?
Okay, so with all of that information combined, moving back here, with all that information combined, what does it tell us that this compound must be? Can anyone share the name of the compound they think it is? Yeah.
3-methyl-butanal.
Ooh.
I disagree.
I think it's a ketone and aldehyde.
You think it's a ketone? Why, when it could be an aldehyde or a ketone, what swayed you that it was one over the other? Nelly?
The 43, the base peak CH3CO+, that would mean that it's bonded to, the CH3 is bonded to another carbon, which is bonded to the O, which means it has to be a ketone, it can't be an aldehyde. Unless it's an ethyl.
But we
And
know it's
also
not
the
an
fact
ethyl
that that
because
same peak is
we know it's not
very,
an
very
ethyl.
high.
Because
So,
that would be too small.
and the other half of our proposed
You
molecule
led me astray.
So you're
has two halves that make that weight. So that's why it's like
you're saying
twice as
because
high.
with the ketone it contributes significant fragments that weigh 43
Yeah.
to the, that's a reason. If we looked at the aldehyde a bit closer and all the ways it fragments, we'd probably find that the fragments off of the
Don't match
aldehyde don't match up with the
Yeah.
mass spectrum.
that was what I found.
So maybe we'll take a look at that in just a second. But this is what you probably should have got, 3-methylbutan-2-um. Now I'd like you to do the following. I'm going to go through the justification, and at this point you can read through the answers on the back of your sheet now, so you can flip those over. Okay, now what I've done is I've broken up my long answer into small paragraphs with titles to my section so you can understand what I'm doing. Okay? Did I make a mistake?
It says ions. The blue underlines.
Oh, not the IOs.
At the end of your
Down.
second paragraph.
Oh,
Word
Yeah.
P,
don't you know about IOs? Okay.
Not yet.
Don't introduce that.
A formula is. Okay.
Exactly.
Okay.
A U-level thing.
So-
Uni. Alright.
These titles in bold, these are just me explaining to you what I'm doing. So in the first paragraph of your report, you always want to start by looking at the IR. And that's what you would do intuitively, right? You look at the IR for what functional groups it tells us about, and also the absence of peaks, so that it can help us narrow down what the functional group is. So I wrote,
What it is, but what it also.
yeah, so I wrote on the IR spectrum, there's a strong, sharp peak. Use those adjectives, right? Strong and sharp at about 1700, and this is indicative of a carbonyl bond. This bond is found in the following functional groups. It could be a carboxylic acid, aldehyde, ketone, or ester. However, there's some bonds that are missing, right? There isn't a sharp, strong peak at 1200, which is what I would expect if there was a C single bond O, so it can't be an ester. And there isn't a broad OH stretch, so it can't be a carboxylic acid. The molecule must either be an aldehyde or a ketone. So we use process of elimination there to reduce it down to what it could be.
Can you give us an idea of what are you looking for achieving excellence?
Yeah, for excellence, you definitely need to mention what bonds are not there. Okay?
Is it possible to get excellence but have the name of the molecule wrong?
No. Yeah. So moving on to the next section, that's all we can do with IR. And for excellence, like I said, you do need to discuss what peaks are not there to help narrow down the possibilities down to what the one or two you think it is. So next paragraph, discuss the number of carbon environments there are in the NMR, and you need to propose a molecular formula, and I'll show you how I did that. So the first statement's pretty obvious. The NMR indicates 4 carbon environments. We see that the peak at 20 ppm is about double the height of the others. So possibly, because the peak is double the height, this could indicate there are 2 carbons in the same environment, suggesting that maybe there are 5 carbons. But I'm not sure yet. I'm looking at the peak height, and I'm saying, hey, you know, one's quite a lot taller. It looks like one's significantly taller than the other, so maybe there's multiple carbons in that environment, but I'm not quite sure. Because remember, peak height sometimes just varies naturally. Yeah.
Is there any way of telling absolutely how many carbons are in one environment? Or are you guessing up until the end?
I'm guessing up until what I'm going to do now. So I say, at this point, okay, I know how many environments there are. And now I say, looking at the molecular ion peak on the mass spectrum, so I'm jumping a little bit just to get the molecular ion mass there. Looking at that peak and seeing that it's 86, this further supports my hunch that there are 5 carbons, and here's why. If there were only 4 carbons, well, 4 times the mass of a carbon, which is 12, right? Plus the 16, why 16? What contributes 16? Yeah. Right, that we know must be there. That only adds up to 64, and the total mass of the molecule is 86, so that's suggesting I have 22 hydrogens, which is an absurd number.
So once again, you're saying, here's why I'm right.
Here's why I think I'm right, that there are 5 carbons. But, okay, what if there are 5 carbons? What if my hunch is correct? 5 times 12 is 60 plus 16, that adds up to 76. And that means the remaining mass of 10 must be hydrogens, and that's a more reasonable number of hydrogens. So I'm proposing, in conclusion, that the molecular formula is C5H10O. Okay? So in that second paragraph, I talked about chemical environments, but I also linked it to the molecular ion to help justify the molecular formula. Cool.
I like this.
So you basically spent that paragraph rolling out 4 carbons
Yeah.
in favour of 5.
Yeah. I'm saying
This
it's
is like the
Yeah.
best debate ever. Like someone's throwing questions at you like, but what if it's this? And you go, no, I thought of this. I thought of this, and here's my proof.
That's exactly it, yeah. And I like this part because you're trying to figure out the formula and you're like, oh, that's an absurd number of hydrogens. It can't be that.
That's an absurd number.
At what point do you stop thinking the number of hydrogens is stupid? Like, what's reasonable? Because
Well-
it's possible. Surely there are things.
Try
that have-
to draw it out. If you have 5 carbons, where are those hydrogens going? You can't, yeah. Or 4 carbons, I mean. Third paragraph, we need to discuss the carbon environments individually and what environment they live in. So when you see that one peak is shifted extremely downfield at 220, this is likely due to a very de-shielded carbon, right? Probably the one in the carbonyl group. So it must be a ketone, not an aldehyde, because it's in that specific region where we see ketones. If you look closely on where it is and match it up on our tables, aldehydes and ketone carbons are shifted slightly differently. Yeah.
It's 1 not labeled, 2 not far enough to label to B220. It's still aldehyde, right?
It still kind of is, yeah.
Yeah.
Which is just
And we're going to use,
It could be. If that, yeah.
we could use the mass spectrum to help justify why it's a ketone and not the aldehyde. So,
It still adds up to that mass.
It doesn't
It still
matter.
works.
It doesn't work.
It does.
No.
moving on. What about the other peaks? We need to say something specifically about those peaks and what their environments are like. Now, overall, I think Johnny was the one who said they're all alkyl kind of peaks.
Yes.
Yeah, sweet. So let's talk about them individually. The large peak at 18 or so, around 20-ish, right? It's indicative of 2 methyl groups in the same chemical environment, right? Oops, where did my thing go? Oh, where'd it go? Here we go. Now the peak at 25 must be a methyl group next to the carbonyl group. So it's slightly kind of de-shielded. It must be the carbon immediately next to that carbonyl group. And the peak at 40 is the one kind of connecting the carbonyl group to the rest of the chain. So we need to propose fragment structures for a minimum of 2 fragments, as I said earlier, or 2 peaks, right? So the mass spectrum shows a molecular ion peak at 86. We can't really propose a fragment because that's just the whole molecule. There's a base peak at 43, and you guys figured out if you split the molecules someplace, you'll get 2 fragments, both with a mass of 43, so they both contribute to that peak. The peak at 15 is a methyl group. The peak at 71 is the fragment you get when the methyl group breaks off, and the fragment of the methyl group is neutral, and the rest of the molecule is charged, and that adds up to 71, so you can propose something for that. So we justified that, yeah, our structure matches up. If we break it in various places, it forms the mass spectrum we see. And in
You've
conclusion,
even used the classical, like, therefore the molecule
Yeah.
must be this.
it matches all the data. It must be that. So that's it. Of course, you don't need these section headings. These are just so you can understand the structure of my response, and I want you to try to emulate that a bit. It makes sense to start with the IR, right? And then go to carbon NMR and use that in tandem with the molecular ion to figure out the formula.
So the IRs kind of stand alone, the last 2 sort of link into
They do. The last 2 link together, yeah.
Right.
Cool. All right.